Hi friends, welcome to the channel Learning R is Fun. In our last video, we have seen some parametric tests, especially t-tests for one sample and two sample. We also seen how t-statistic can be used. This video will be covering non-parametric tests. As we know, non-parametric tests do not make any assumption on the population or its sample size. In general, the conclusions from these non-parametric methods are not as powerful as parametric ones. In our example in RStudio, we will see one same problem will approach by both non-parametric and parametric method. But in non-parametric methods, we have got fewer assumptions and it is flexible, robust, as well as it can be applied to non-quantitative data. In today's session, we will cover 4 non-parametric tests: sign test, Wilcoxon sign rank test, Mann-Whitney-Wilcoxon test, and then Kruskal-Wallis test. We will take one sample from the real life data in the last case, and then we will find out how this test is useful to us. Let's go to RStudio. For today's session, I have got 2 scripts. I will load them. We will start with the first test. It is sign test. It's also known as binom test. Basically, binomial distribution has got 2 possibilities. We have probability P and probability Q. Probability P for success and Q for not success. P plus Q is 1. Let's get on with the problem. A tea company has invented a new blend and wants to find out whether it will be as popular as their previous blends. It arranges 72 participants for testing. Each participant tries both drinks in random order before giving opinion. It turns out that 20 of the participants like the new tea better and the rest prefer the old one. At 0.5 alpha, that is significance level, can we reject the idea that 2 teas are equally popular? So question is whether there is a difference or not. So let's ask her what is this binom test. Exact binomial test. It is from the stats package. Performs an exact test of a simple null hypothesis about the probability of success in a Bernoulli experiment. Jacob Bernoulli, a 17th century Swiss mathematician, conducted certain trials and his experiment on tossing of coin and the resulting finding led to binomial distribution, and that binomial distribution generally we call a Bernoulli distribution also. So here binom.test is the simple R function and we give 2 values. One is 20 and 72. 72 is what? 72 is the participants, out of which 20 have said the new drink is better. So let's ask R. So binom test has been done, it's exact binomial test, and we are getting a probability 0.000 which is less than 0.05, so we have to reject the null hypothesis. Here we have to see how the number of samples we take is very important. So in this instant case, we have taken a call based on the rejection of the null hypothesis. But suppose I take a proportion from this, 20 divided by 4 and 72 divided by 4. I am getting 5 and 18. I am giving the same proportion. However, this binom test is giving me the probability of 0.09, which is greater than 0.05. Therefore, we accept the null hypothesis. In this case, again, we calculate and we get a 0.01 which is less than 0.05, so we reject the null hypothesis. So what's happening? We have to take fairly large number of samples to get a decision. Once you get a higher number and then you increase the numbers, it's not going to change. So we can see, for example, binom 2072, what we got is 0.00, that is we rejected the null hypothesis. Now let's do the same test with a larger number. Binom test, I will multiply this by say 10, so I will get 0, and here also 10, so I get 720. Let's ask for the p-value. I am getting a less value of p. In the previous case, I got again a p-value which is less. And now here also it is 0.05, it is becoming much less. So, if you increase the samples now in the same ratio, it's going to give you lesser and lesser p-values. So, to start with, you should not have minimum samples. You should have fairly large number of samples to get on with the test. Okay, now let's go for the Wilcoxon signed rank test. Here, two data samples are matched if they come from repeated observations of the same object. In the last video, we have seen a paired t-test understanding. Of course, we have not done any problem. Here, we will be able to do it. Let's look at the problem. In the built-in data set named IMMER, the barley yield in years 1931 and 1932 of the same field are recorded. The yield data are presented in the data frame, columns y1 and y2. This is a problem. Without assuming data to have normal distribution. Test at 0.05 significance level if the barley yields of 1931 and 1932 in dataset IMMER have identical data distributions. This is a problem. So we take the mass package, then we have to ask what is IMMER, then we get to know about this data set. Yields from barley field trial, IMMER data from 30 rows and 4 columns, 5 varieties of barley were grown in 6 locations, each in 1931 and 1932 years. Data is available. So location where, that is the variety of barley, Manchuria, Swensota, Velvet, Trebi and Peatland. Y1, that is yield in 1931, Y2 yield in 1932. So let's look at the data. We have got 5 can say varieties. M, S, B, P, T, P, again it repeats, and then we have got different locations. We have got yield of Y1 and Y2. In such cases, we go for paired is true because in the same land only this was done again and again. So, Wilcoxon test will apply. So, we are getting a true location shift is not equal to 0. That is the alternative hypothesis, and we will see the p-value which is 0.005. Therefore, we have to reject the null hypothesis. And when we are saying true location shift is not equal to 0, it compares the distributions and finds the medians are not in the same place. That is the finding basically. When we say location shift, it is indirectly telling that the underlying data has got different medians. So, we conclude barley yields of 1931 and 1932 are not identical. Okay, because we have rejected the null hypothesis, we have accepted the alternative hypothesis. The same test we can do with t-test also, because quantitative data and a problem has been given as without assuming normal distribution. So, that's why we did non-parametric test. To do parametric test, we have to take the assumption that they are normally distributed, and let's see the result of the pair t-test. Here we have to say paired is true and the two data x and y we have to give. And here also we are getting a value less than 0.05, therefore we reject the null hypothesis, and we also conclude the same thing. But this test is a more powerful test when compared to the previous test. Let's move on. There is a Mann-Whitney-Wilcoxon test. Here two data samples are independent if they come from distinct populations and the samples do not affect each other. Using this theorem test, we can decide whether the population distributions are identical without assuming them to follow the normal distribution, because non-parametric we don't assume. So as an example, empty cars MPG will see, and then empty cars AM. So these are the MPGs and these are the automatic transmission true or false values. Now between these, whether they are independent, that is there a connection between the automatic transmission and the miles per gallon, is what we have to find out. So the problem is also worded like this: without assuming the data to have normal distribution, decide at alpha 0.05 if the gas mileage data of manual and automatic transmissions in empty cars have identical data distribution. So here we use the Wilcox test, and then MPG as a function of AM, and data is empty cars. So we are getting Wilcoxon rank sum test with continuity corrections, and we are getting a value 0.001, which is less than 0.05. We reject the null hypothesis. So there is some difference. That is, there is an effect of the transmission and mileage. Or we can say the gas mileage data of manual and automatic transmission in empty car are non-identical. Okay, for the next test, that is Kruskal-Wallis test, we have to go for next program, air quality Delhi. Let's clear the screen. Here we are taking the data from Kaggle website, which is an important website for data science students and enthusiasts. The problem given here is, without assuming the data to have normal distribution test at 0.05 significance level, the monthly AQI in New Delhi has identical data distributions during the year 2019. And now we can take the data using library reader, and then we'll store the data, and this data I have already downloaded, and therefore I am taking from my own PC. So I am storing that in ct_day_csv. So let me view this data. The data is like this. We are getting the cities, we are getting the dates 2015 onwards, and we are getting dates up to 2019 basically. 2020 also we have got 2018, and then we are getting up to 2019. Then we got various parameters, and we are interested in the AQI, which is the air quality index. Okay, now we'll load tidyverse, lubricate, and then we'll ask the structure of this. So we are getting a structure like this. These are the columns: city, date, etc. Now from this, what we'll do, we'll select only for city Delhi, and year is 2019. So we use Magritar, basically the pipe city day CSV. This will pass on to the filter, and here we say city is Delhi and year is 2019. So we get a DF which is only for Delhi, and we'll ask a summary, and we are getting, and we are asking for year 2019 only. So we are getting from January onwards up to December in the case of date. Similarly, other data also we are getting. You can see the air quality index here 66,659. So there is a huge variation in the air quality index. Now let's do a small plot, and we are seeing for January onwards up to December the AQI, how it varies. That is, in each month there is some variation. The second month, this is the third month, like that. Now let's ask R, what is Kruskal test? Kruskal test performs Kruskal-Wallis rank sum test of the null and the location parameters of the distribution X are the same in each group. We have got now monthly data, and we have to see whether the distribution in this monthly data is same. So let's see using a box plot also, AQI as a function of the month. Data is same, and we will give colors, rainbow colors, and then we can see there is a distribution. You can say in the month of November, most of the days we had more than 350, and in the month of December we still had higher AQI. Again it continued in January, and slowly it reduced in February, March. So there is generally in the winter months the AQI is very high. And now let's do the Kruskal test, AQI as a function of month. So we are getting a p-value. This is done using chi-square distribution, and p-value is very less. Therefore we have to reject the null hypothesis, and therefore the distributions are non-identical, which is very much visible from the box plots also as well as from the other. Now the same problem we'll see slightly differently. Now what we'll do the comparison of the AQI for the over the years to see whether any particular year has got a different distribution. So we'll do the same thing. Instead of DF, we'll now have DF December, and filter will set cities Delhi, and year is year of date in 2010 to 2019. Means we take different years. Actually only 15 to 19 is there, but anyhow I have given this. Then month is 12. So only December data for these years we have taken, and we'll store them in DF December. Let's do the plot, and the plots also give us some indication. Now we'll do the test. We are getting a p-value 0.001, which is less than 0.05. Therefore we have to reject the hypothesis that the AQI across the years 2015 to 2019 remained same in December. That we reject, and therefore there are differences. We can also see here in 2016 and 2018 we see that there is a peak. Alternative years, whether there is a peak, that we have to get additional data and then examine that. So in these 4 tests we have done without any assumption of the population data. We have used the non-parametric. Thank you for watching, and see you in the next video.